Here I will try to simulate the behavior of a model under base excitation, basically a quarter car model, a mass and spring and a damper running on a sinusoidal road, simulating base excitation y of t, and the equation of motion is right here. So first I will start by rearranging the equation of motion so that the acceleration x double dot, that's the state variable, the motion of the mass m, which is the one I'm interested in, is on one side. Y is actually an input, so that will be defined by the user. So I will start by first adding my state variables x double dot and x dot. Start by using an integrator, another integrator right here. Connect the integrators. The input to the first integrator is x double dot, so I'm going to call it ddx. And the output, after integrating the acceleration, I will end up with the velocity dx, and the output is going to be the variable x. Now, x double dot from here is the sum of three quantities. One quantity in the brackets here, that's the input, cy dot plus ky. We'll assume that that's one quantity, an input, and two negative quantities, negative cx dot and negative k. So I'm going to need a sum block right here. So the sum of these three quantities will be the acceleration. I'll have two vertical bars, a positive sign for the positive input here, and two negative signs for negative cx dot and negative kx. Now, first negative quantity is cx dot, so I'm going to connect that right here. The second is negative kx. Now I'm going to need two gains for c and k. So here's a gain. Connect that in line with the x dot, and this gain will be c. And then another gain here, let's call it k, in line of x. Let me add a scope to see what x is. Now, one last step is x double dot is the sum is divided by m, so I'm going to need another gain right before x double dot. I'm going to call this gain 1 over m. Now, let's go to the input quantity here, cy dot and ky. The input is sum of two quantities, so I'm going to need a sum block. Here's sum. I'll just rearrange the ports, top and side ports. Now, the input is a sine wave. So I'm going to need a source that generates a sine wave. So we go to sources and scroll down to sine wave. Here's sine wave. The output of this sine wave is y. Now, y is multiplied by k, so I'm going to need a gain, k, Now I need y dot, so I have an error here because I've used k already. So to run around that, I'll add space k. Now I need y dot, so I'm going to need a derivative block. Go under continuous. The first block up here is derivative. Alright, so connect that to y, and the output is y dot. Now here's y dot, but y dot is multiplied by c, so I'm going to need another gain right here. I'm going to call it space c so that I don't get name conflict. And here we have ky plus cy dot. Now let's put numbers here. The mass is 100 kilograms, so this is 1 divided by 100. C is 200 Newton second per meter. Gain K, the stiffness is 10,000. 10,000 for K right here again. And 200 for C. The amplitude of the base excitation Y is 0.1 meters, and the frequency, it's 1 right here, so we can keep it at 1 or maybe change it to slower, 0.5. Okay, and in this scope, let me also output y, see, to compare the input and the output. Sorry. Okay, right here now the first output is X and the second is Y. Double click and hit play. Alright, and here's the response. The input is the blue line, the sine wave, and the response is the yellow line. You can see here in the beginning the homogeneous solution causes little deviation here until the damping takes effect and the homogeneous solution goes to 0, and what remains will be just the forced response, which is in this case very close to the excitation amplitude. Now if I change the damping or reduce it to 100, you will see that the natural response takes longer time to disappear. Right here it starts to become more visible because we have less damping, so it takes more time to die to 0 because the power in the exponent, negative zeta omega n, is now smaller. If we change the frequency of the input, let's see what's going to happen. Right here, increase the frequency to 1. Alright, and see the natural response here is quite clear. It takes a bit more time to go to 0. So this is how we simulate a base excitation problem. The excitation terms or excitation blocks on one side, and the equation of motion itself separate. Now we can rearrange this so that we can put the system all together in a subsystem here, and let's call it car model. Okay, and here this side I can put it in a subsystem and say call it road. Okay, now I have clean model here. You can name the inputs here, maybe profile, and the output here is road. Go up one level, and here's your road block. Here the input, you can name it road, and the output is X. Go up one level, and here's my complete model of base excitation problem, basically quarter car model and a sinusoidal road.